So magic numbers and so how many elements are there in each period? So first period is a very short period. Got it? Why it is considered to be very short period, Nabila? First period?
Because
Hmm.
the outermost shells are very low.
Just two elements, hydrogen and helium. Because the first shell is being filled in the first period, okay? So how many elements are there which are just electron in the first shell? Just two elements. First element is the hydrogen, second element is the helium. 1s1, 1s2. And with that, you have the first period complete. Got it?
Yes.
Once you have the first period complete, then what you do? 1s is complete. From lithium, what you do? Lithium is the third element. Li. So what should be the electronic configuration? So 1s was already complete in the first period. Now you have 2s.
One.
2s. Okay. So it will be in the S block element. Got it?
Yes.
S block element, first group 1. Because it is having one electron in its outermost shell. And this is second period. Got it?
Yes.
S belonging to S subshell. Group 1. That we have discussed, right? Next is beryllium. Beryllium is 1s2 and 2s2. Now you need to put one more electron that is going to be put into 2s, right? So these are two S block elements from the second period. Then because the second shell also has the P subshell, and the P subshell is having 3 orbital and it can hold how many electrons? Boron 2, boron, carbon, nitrogen, oxygen, chlorine 2, neon, right?
Yes.
You have 1s, 2s was already filled up to beryllium. Now you have 2p from 1 to 6 electrons. Neon has having 6 electrons. Got it?
Yes, sir.
Is it clear or not?
Yes, sir.
So this is the second period. So how many elements till now we have put into the second period? 2 elements in the S and 6 elements in the P. Got it? Why there is no any element belonging to D block in the second period? What could be the answer, Nabila?
Could be from.
Pardon?
No, sir, they're not in D.
Because second shell doesn't have any D subshell. Okay. Second shell is having only 2 subshells, right?
Yes, sir.
So we don't see the D block element in the second period. So this I hope is clear to you, right?
Yes, sir.
Okay. Third period, how many elements? 8 elements. But tell me, the third period is having uh, how many subshells are there in the third shell? How many subshells? 3s, 3p, 3d. Got it?
Yes.
But so this can have 2 electrons, this can have 6 electrons, and this can have 10 electrons, but we have only 8 elements, and only element belonging to S block and P block in the third shell, in spite of having D subshell. Why is it so, Nabila?
Mm, not sure.
So actually third shell is having D subshell, but when it will be filled?
Uh,
Just look here. 3S, 3P, 3D. Are they filled in this way? Or I need to change something? 3S, 3P, right? Go back. 3P.
Yes, sir.
Then you have 4S. Okay. Then go back to 3D. Got it?
Yes, sir.
Is it clear or not?
Yes.
So actually you have 3S, 3P, 3D. But 3D is being filled after 4S. Got it?
Mm,
So you do not have, so if you put 3D, you will have 18 element, but you don't have 18 element because 3D is filled after 4S. This is a very important question. You need to keep in mind. Got it?
Yes, sir.
Okay. So we have discussed some of the properties. So these are short periods. You can write them. And the other periods, other two periods are long periods. Got it?
Mm,
Why they are considered to be long periods? What's the reason?
they are more in the balance.
So tell me, what's the reason? Why they are considered to be long period? Because 18 elements are there and they have 3S and they have S subshell, P subshell, not only SP, D subshell is also being filled into them, right?
Mm,
Sixth and seventh period, F subshell is being filled, but you can notice that the look 3D, 3D, 4P, 5S. 5S after 5S, you will have 4D, 5P, 6S. Okay. So of 6S with the 6S, you will see that after 6S, 4F will be filled, right? Is it
mm,
clear? So sixth period and the seventh period will have the F orbitals being filled. Got it?
yes.
But that F orbitals are 7 and they will have 14 elements. So if we try to place the 32 elements here, the shape of the periodic table will be very wide and it will not be, we will not be able to study it properly, interpret it properly. So what is done is this F block elements are placed at the bottom. There are two series, 4F series and 5F series. Got it? So just
Okay.
let me open the periodic table. Okay. Can you see the table?
Yes, sir.
So look, fourth period, sixth and seventh period will have 32 elements. Okay, that 57 to 71 elements. Look, that red one and the green one are placed at the bottom. Is it clear? Of the periodic table,
Yes.
right? So why they are placed at the bottom? What's the reason?
Because they're not, they're having more
Otherwise,
than.
they are having so many elements. Suppose if you try to place them here in this place, it is going to be quite cumbersome task, right? The periodic table, the last 6th and 7th period will
Yes.
become very wide. Got it? So
Yes.
this is called 4F, this is called 4F series elements, right? Because of each subsequent element, the 4F subshell is being filled, and this is 5F, right? The first element is lanthanoid. This is D block element. So these all these elements after La, lanthanum, they are called lanthanoids, and 5F elements are called actinoids because the first after the name of the first element. Can you see the lanthanum and actinium?
Yes, sir.
Got it? So this I hope is clear. They are also called inner transition series element, right?
Okay.
Inner transition series elements are, they are D and F block element. D block element are transition series element, F block are inner transition series. Okay.
Yes, sir.
F block will have 14 elements. F block will be filled up in the 6th and 7th period. You can see the 6th and 7th period, but they are not placed there, they are placed at the bottom to maintain the shape of the periodic table. While the third period is having the D subshell, but the D block elements are not in the third period. Look here, sodium, magnesium, you do not have the D block element because 3S, 3P, 3D. 3D is being filled after 4S. Okay, so you have the 4S being filled potassium, calcium, and then you have 3D elements starting from scandium to titanium, vanadium, right? Up to same. Okay. One 3D is filled, you have 4. So just what you can do is you can you can just write the order of energies. Is it clear?
Yes.
Of the subshells which are being filled. Okay. So this is the and like 1S, 2 elements, then 2S and 2P. In the second period, 8 elements, then 3S and 3P, 8 elements, then 4S, 4P. Got it? How many elements? 10 plus 8, 18 elements, then 18 elements, right? Like that, you can write the order of the subshells and the number of elements which are being filled in each period. So I hope this is clear to you.
Mm.
Got it?
Yes, sir.
Okay. So now we need to start with the periodic properties. So what do you understand by periodic properties, Nabila?
Each of the different periods will have different properties.
Yeah, actually the trends as you are moving from left to right in a period, how the size of the elements are changing. Or if you are moving down in a group, how the size is changing. Other properties are also there.
Yes, sir.
Ionization energy. Okay. So mostly what we are going to do is we are going to discuss some of the periodic properties like atomic and ionic radius. Got it?
Yes.
Then you will have some property known as ionization energy. And the other properties are actually metallic character and all are related from these properties. Then you have electron gain enthalpy. Or electron affinity. And electronegativity. Okay. So, and with the electronegativity, you try to compare other properties. So, basically, how the properties are changing, how the size of the atoms are changing. Okay, that depends upon the effective nuclear charge. Okay. So effective nuclear charge, actually it is known as Z effective. Right? It is going to control that how the electrons, the outermost electrons are getting attracted towards the nucleus. Okay. What do you mean by nuclear charge? First of all, tell me, Nabila.
Like the charge in the nucleus.
Yes, it is because of the
Nucleus.
protons or neutrons. It is because of protons only, because only
Yes.
protons carry positive charge, right? So let's say, suppose example, you have sodium. Right, sodium, I should write it in this way. Sodium, in the atomic number is 11. It has 11 protons and the mass number is 23. This is the number of protons. And if it is Na plus, then you need to remove one electron. Okay. Normally, if it is a neutral atom, the protons and electrons are same. Got it?
Okay. Yes.
So now you have a nucleus. Nucleus will have a charge of 11 protons. So proton has plus E charge. Okay. Electron is minus E, so proton is plus E. Same magnitude, but opposite in sign. Electrons are negatively charged, protons are positively charged, we know. Okay, so this is the first shell, and it will have 2 electrons. And you have a second shell. So that will have have 8 electrons. Total we need to put how many electrons? 11. Okay, till now it's 8. So till now we have put 10 electrons. 10 electron, and this is the outermost 11th electron. Okay. Mostly this electron is the valence electron. This is the most important electron because this electron only participate in bonding. Got it?
Yes, sir.
It can participate in bonding. It can be lost. It can be okay. All the properties will be governed by this. Right? So how much this outermost electron is feeling the attractive force? Is it because of the 11 protons or more than the charge of the 11 protons or less than the charge of 11 protons?
Less than.
Less than the charge of why?
Yes,
The
it has.
nucleus has 11 protons. Okay. So this outermost electron, how much charge it is feeling? Exactly same as the charge of the 11 proton, exactly equal to the nuclear charge, less than the nuclear charge. What this electron is feeling?
Less than.
Yeah, less than the charge of the 11 proton. Yes, why?
Because it has to be
That
distributed.
is correct. Because
It has.
actually suppose these 11 protons are attracting, right? But
Yes.
there are 10 electrons in the bit in middle. Got it?
Yes.
Is it clear or not? So what they are
Yes.
trying to do? So what they are causing repulsion. So actually the net force felt by this outermost proton is known as Z effective. That is the effective nuclear charge. It is the nuclear charge minus shielding. So what do you mean by shielding or screening?
Mm. I'm not sure.
It is the repulsion caused by the inner electrons. Got it?
Mm.
Shielding is nothing but what this is trying to attract. Let's say suppose if we have this is trying to pull the outermost electron, but these inner electrons are trying to repel that outermost electron away. Got it?
Yes, sir.
So shielding is the repulsion caused by the inner electrons, or screening is the repulsion. It is the repulsive force caused by the electrons of the inner shell. Got it?
Yes, sir.
So basically, you should not consider the total protons, but you should consider the inner electrons also while considering in order to decide the properties, periodic properties or the variation of the properties of various elements. You need to consider effective nuclear charge because that is the actual charge, actual force of attraction felt by the outermost electron. Is it clear or not?
Yes, sir.
Okay, great. So let's start with the Z. So when we will call it as effective nuclear charge, and I hope you understood that is the nuclear charge minus the shielding caused by inner electron minus the repulsion caused by the inner electron. Okay. So first we are going to discuss atomic radius. This this is basically the size, atomic size. This tells how big an atom is, how small atom is, and a small an atom will be. Got it?
Yes, sir.
It is the radius, atomic radius, right? So what is basically it is the distance of the center or the nucleus from the outermost shell or the valence shell. So this is quite simple, right?
Yes.
Atomic that you can also write it very clearly. This is the atomic radius, okay? But the problem is, okay, that it is not possible to find. If I give you, suppose if one atom is given to you, will you be able to find the size? Okay, it is not possible. It is
Yes.
because why? One atom, if somebody give me one atom, I will say, okay, I can find the size of the atom, how big or how small it is. Okay. But why am I saying so, Nabila, that if I give you single atom, it is not possible to know the size.
Each atoms can have different sizes. So
Mhm. Suppose sodium atom I gave you, single atom, let's say, but it is too small. Actually, I can't give you, but imagine if you get one sodium atom, single sodium atom. How will you know what its size is?
from the configuration, electronic configuration.
Hmm. Actually, it is impossible to find out the size of a single isolated atom.
Mm.
It is because here in my case, I have shown you the outer boundary. Okay, and I am showing that from the center to the outer boundary, you can have the size. Okay, but practically, this is wrong because atom doesn't have a fixed boundary. You can't see its boundary. It's an electron cloud. Okay, so electron cloud can have can can have a lot of distance. Okay, from the center. So basically, actually, that doesn't electron cloud doesn't have that sharp boundaries. So that is the problem. Okay, so it is impossible to find out the size of a single isolated gaseous atom because what is the reason? The electron cloud doesn't have sharp boundaries. By which I can make out, okay, here I have drawn a circle, right? Actually, uh, no sharp boundaries are present, so I can't make out where the atom ends, right? So how to check the size of an atom? You can check the size of an atom. It is if it is along with the other atoms, okay, and you can check the size if it is along with the other atom, and if an atom is not isolated single atom, but you can measure that if atoms are present in a group, okay, and if they are close to each other. So how close are they? That can let you imagine the size. Got it?
Yes.
Suppose if the small atoms are there, they will come very close to each other. Got it? So what you do is you try to take the distance between the two atoms and take the divided by two, half that distance. That will be the size of the single atom. Are you getting my point? So you isolated atom, if I give you, you will not be able to find the size because it doesn't have a sharp boundary. So what you do, you take large number of atoms, okay, in solid state. Okay, I will tell you. So you try to figure out the distance between the two adjacent atoms, okay? And that distance you divide by 2, that will give you the size of the atom. That distance definitely is going to tell us about the size of the atom, because if the atoms are very big, okay, surely the size is going to be large, okay? And if the atoms are small, they will have small distance between them. Okay. So exactly you measure the distance, and how you measure the distance, that is by X-ray. Okay, there are various techniques by which you measure the distance between the two nucleus. You half it, and that will be the size of that. Okay, so you will have atomic and ionic radius. Atomic radius first we can discuss. Okay. So atomic radius is basically, there are 3 kinds of radius. Okay, covalent radius, metallic radius, and van der Waals. Covalent radius is basically, as the name indicates, it is 1/2 of the distance between the two adjacent covalently bonded atoms in a given molecule. Are you getting my point?
Yes.
So just so suppose if I give you molecule, can you give me some example of molecules?
Mm.
Let's say suppose if you have hydrogen molecule, got it? H2. So hydrogen atom, normally we draw it like this, okay? Normally if I take the single atom, I draw it. So you will think that, okay, it has a fixed boundary, but it doesn't have fixed boundary, that boundary is not visible. So what you try to do is, you take H2 molecule, okay? Is it clear or not? So H2 molecule, so it will be like this. And you try to measure the distance between the two centers. Is it clear?
Yes.
And you just, this you can do by X-ray, because in X-ray you can see the nucleus, and you just half it. Okay. This distance of the hydrogen is 74 picometer. What is picometer? it's a very small value, 10 to the power minus 12 meters. Because we are measuring atoms, they are going to be very small, okay? And the distance is also very small. Okay, so this comes out to be 74 picometer. So what is this? These are covalently bonded. You might have seen in your class 10 that covalent bond is formed by sharing. Got it? So this is hydrogen molecule where the two hydrogen atoms are bonded to each other, as you can see here, and the distance is experimentally measured. That is 74 picometer. Got it?
Yes.
And what 1 picometer is 10 to the power minus 12 meters, right?
Yes.
So you try to get the radius. What should be the radius of hydrogen atom? If the distance between the two atoms is 74, how you get this? This is not the size of one atom. This is the distance between them. This. So how you get the size of one atom?
Yeah.
You divide it by 2. You just half it. Okay.
Yes.
Is it clear or not?
Yes.
So if you half it, it will give you this distance. Okay. And it is the when you half of DH2, right? It will be 37. So it is the covalent radius of hydrogen atom. Are you getting my point or not?
Yes, sir.
Let's say chlorine molecule if you have taken. So distance between the chlorine atoms in a Cl2 molecule is 198 picometer. Clear? What is the radius, covalent radius of chlorine atom? How much?
90.
Yeah, just half it. 90 4 picometers, right? Is it clear?
Yes.
99. Got it. So 99 picometer it is. If you double it, it will be 190. So just half it.
Yes.
So I hope that is clear to you. Got it. So this is the radius of chlorine. So, but actually you need to understand that the way in which you are getting the radius by this method, it is going to be bit smaller than the actual size. Let's say suppose the actual size of the chlorine is this. Okay. And the actual size of another chlorine is this. Right? So how you are getting the distance which you are measuring is this. And if you are half making the half of this distance, okay, you are measuring this distance actually, but the size is basically up to this point, outer. But the problem is you can't see the outer boundary, right? That is the problem. Yeah, you can't see the outer boundary. So that is the main problem. So what you do, you just measure the molecule, you take the molecule of the distance. That is basically the equivalent radius. So I hope this is clear. Next is metallic radius. What do you mean by metallic radius? As the name indicates, you are measuring the distance. How you are measuring the distance? It is 1/2 of the distance between two nearest or adjacent. So metallic solid, can you give me example of some metallic solid?
Um,
Metallic solid.
iron,
Metallic solid, like you have iron, that is a metallic solid. Got it?
yes,
Okay. Gold. Gold is also solid. Copper. Right? So you take a metallic solid, you put X-ray. With the X-ray, you get the metals, the atoms as appear as dots in X-rays. Okay, the nuclei. So what you do, you take the two nearest atoms and you divide the distance by half, by two. So one half of the distance. Is it clear?
we
Got it?
divide by 2.
Yeah. Divide by two. So that is, so if you take a metallic solid, this is metallic solid. So nearest atom, this is the distance. You divide it by two. Got it? So when you divide it by two, you will get the idea of the size of the one atom. Is it clear or not? Okay. Metallic radius will be larger than the covalent radius because in a metallic solid, the atoms are farther. In a covalent bond, only two atoms are joined and covalent bond is stronger. So the atoms are near to each other. Though it depends on other factors also. But if you take the same element, if you try to measure the covalent radius and if you try to measure the metallic radius, the covalent radius is shorter, will be shorter than the metallic radius. So Nabila, is the definition clear?
Yes,
So you do half, you take half of the distance, right? Okay. So I hope this is clear to you. Got it. Van der Waals radius. So metallic radius is larger than the covalent radius, right? Then you have van der Waals radius. So that is a problem when that you do not see that all the you see that all the atoms don't participate in bonding. Okay. Is it clear?
yes,
All atoms don't participate in bonding, right? That you know. And there are so we should find some way by which we can get the size of the atoms which do not form any kind of bond. In covalent radius, we can find the size of those elements which are bound by covalent bond. In metallic radius, we can find the size of those elements which are metallic in nature and which exist as metallic solids. So in a solid, you measure the distance between the two nearest atoms, you half it. Van der Waals radius is for those elements which do not form any bond. Can you give me example of elements which do not form any kind of bond? which do not form any kind of bond.
Any form of?
Pardon?
Can you repeat?
Noble gases, right? Noble gases, they do not have any tendency to form bond. Got it? Is it clear or not? Noble
Yes.
gases have complete octet, that we know. Okay, and because of the complete octet, they do not have any tendency to combine with any other element, right? So this, I hope, is clear to me, right? Random on radius. So random on radius is used. So how, what distance are you going to check if they are not forming any bond? What distance you are going to take? Because we need to take the distance between the adjacent atom and half it, that will give the size. So if they are not bonded, so what you will do? You are going to take the substance in the solid state at a very low temperature. Got it?
Yes.
So when you take it in the solid state at a very low temperature, the atoms, and then you put X-ray, so you will see that there are atoms which are nearest, the two dots which are nearest that represent the two atoms which are closest. Okay, to take measure the distance in the solid state. Why in the solid state? Why not in the gaseous or liquid state? Why it is necessary, Nabila, to take it in the solid state?
Not sure.
A solid state, because gaseous state, the distance is not fixed. If I take a gas, the two molecules are continuously moving here and there, right? And the distances are very large. Okay, two atoms of gases can be at this distance or at this distance. Okay, right? Okay, they can be at the one can be at the this end of the room, another can be that end of the room, right?
Yes,
So
sir.
if I measure that distance and if I half it, my atom will be this much bigger. That is absolutely incorrect, right? Got it?
Yes, sir.
So what you try to do, you need to first cool it, you need to solidify it. If the atoms are not forming bond, you need to solidify it. You need to take the substance in the solid state. Okay, so in the solid state, okay, then you make sure that okay, they are closest to each other in the solid, okay, because they are tightly packed. So there you measure the distance between the two atoms. Okay,
Yes, sir.
let's so van der Waals radius is the 1/2 of the 1/2 of the distance between the nearest non-bonded atoms. In solid state. Got it? So just you can note down, you can also use your mobile to take the screenshot, or you can make a PDF, right? Let me know if something is you missed to note down or take the picture. Okay. Is it clear or not? So let me show you how it varies. Okay, with a diagram. Chlorine is there, right? Okay. So chlorine is basically Cl2 molecule. I have shown you. Let's say this is Cl and this is Cl. Got it? So this distance is X, right? These are bonded or non-bonded? What you feel? These are bonded
Yeah.
because bonded atoms are, yes, they are bonded. They come and connect with each other. They are bonded. And suppose chlorine is a gas, if we try to solidify it, there could be other atom, molecule of the chlorine in the solid state, which can come close to it. Okay. In the solid state only it can happen like this. Is it clear?
Yes, sir.
The distance between the two nearest atoms, non-bonded atom in solid state, they should belong to different molecules. Because within the same molecule, X, okay. So X by 2 is the half of the distance between the bonded atoms. Okay. That is the covalent radius. Got it? But
Yes,
if
sir.
you take the two atoms which are not bonded to each other, the two chlorine atoms, Y, that is the distance is Y. Got it? And this is Y by 2.
Yes.
Y by 2 will be around this much. Okay, this distance will be Y by 2. So it will be slightly more because they are not bonded. So they will not exactly bonded atoms come like this. Okay, they come close to each other. Their electron cloud merges with each other. Non-bonded atom actually they come close in the solid state, but they stop at certain distance. Okay, because there are some repulsive forces also. Okay, so this Y by 2 is going to be the van der Waals radius. Is it clear or not?
Yes, sir.
So it is going to be more than the actual size of the atom. Okay, so size actually covalent radius is smallest, metallic radius is larger than the covalent radius. Then you have the van der Waals radius, which is the two in the solid state between two non-bonded adjacent atoms. Okay. Got it? I hope this is clear to you, right?
Yes, sir.
This is the difference. So how the size is varying
Mm.
as you move from left to right. Now the periodic trends, right?
Yes.
So how the size varies as you move from left to right. Size you can compare covalent radius for all of them. You can compare metallic radius. Okay, anyone you can take. Got it? So how the size is varying?
Increase.
Yeah, periodic variation of size across the period from left to right. So as you move from, let's say, lithium, beryllium, how the size is going to change. Got it? Periodic variation of the size across the period. I hope you understood the meaning of this. We need to figure out how the size is changing from left to right. Got it? So what should we say?
Left to right, so the left one is smaller than the right one.
So how the electrons are getting added, right? First we should think about that. This is 2s. So you have 2p2, 2p3, got it? 2p4, 2p5, got it? And then 2p6, right? And in the neon. So what should we say? Left to right across a period, whether the electrons are getting added to a new shell or the same shell. How the electrons are getting added?
To the same shell.
In the same shell or in a new shell? Tell me.
New shell.
No. In the second shell only they are adding. 2s2, 2p1, 2s2, 2p2, right? The second shell only they are adding, right? It is not the third shell because we are still in the second period. Got it?
Yes.
So if you are in the second period, electrons will be added to the same second shell. And not only electrons are added, the protons are also added. So new shell is not being added, right? Left to right. So I should write electrons are added. They are added to same shell. And inner electron cause more repulsion than the electrons of the same shells, right? So due to which they do not repel each other. Number of protons will increase from left to right. Okay. Or I should say that so suppose if you have, let's say, one electron in the valence, you have two electrons in the valence. Got it? So they will feel more attraction inward. If you have three electrons in the valence, got it?
Yes.
They will feel further more attraction. Four electrons and four protons, the force will be much stronger. Got it? Are you getting my point or not?
Yes.
As you move from left to right, electrons are added to the same shell. The protons are also increasing. Electrons do not repel each other very effectively because they are in the present in the same shell side by side, so they will not repel each other. They will feel more and more attractive force. Okay, so the outer shell is getting more and more attracted inwards. What will happen? The size will decrease. Got it? Is it clear
Yes,
or not?
sir.
Size will decrease.
Yes,
Right?
sir.
So just can you conclude for me what happens to the atomic radius as you move from left to right across the period, Nabila?
The size decreases.
Just size decreases. What is the reason?
It's
Exact reason
because
for the decrease in size?
the valence shell's electrons will attract to the center. So it will
No new shell is added. Okay.
Yes.
Shell remains second period, second shell, third period, right? Third
Yes.
shell like right? No new shell is added, right? So if no new shell is added, electron are added to the same shell.
Yes.
So if that is happening, what happens? Right? Uh, Attractive force will increase because more and more electrons are coming and more protons are coming, so size decreases. Okay.
Yes.
What is the trend for the size? Is it clear?
Yes, sir.
Okay. Great. But the neon will have very large size. Okay, all of a sudden, because neon actually is a noble gas. Okay, and it's
Okay.
not bonded to any other element. Noble gas do not form any bond,
Yes.
smaller noble gases. So for them, the van der Waals radius is estimated normally. So that is already mm, comes out to be largest, right? Is it clear?
Yes, sir.
Okay. Next is let's say suppose if you move down the group, what happens to the size as you move down the group in a period in a group? Variation of size. So what happens? Let's say suppose if you have lithium, okay,
Okay.
lithium is two electrons in one s and 2s is having single electron. Sodium, potassium is the 19th element. So I'm not writing the inner electronic configuration. Got it? So what you are observing as you are moving down in a group?
New shells are not found.
And new shells are being getting added. Okay.
Mm.
This is the second period, third period. fourth, fifth.
Hmm.
So what do you expect from a size, pattern of size?
To decrease.
Will it be more? Will it be less? What will it? As you move from lithium to rubidium,
It will be less.
less. Why? The
Because
size depends upon the outer shell. As you are moving down, will it be more or less? You have second shell, right? Then you have third shell. Okay, outer electron is placed in the third shell, 3s. Then fourth shell, right? Fifth shell. Okay. So what is happening? As you are moving down, the outer shell is increasing. Got it?
Yes.
Okay. So new shell as you move down. A new shell is added in every subsequent element. And the new shell will be outer shell. Okay, new outer shell. It will be larger. Got it? Because if you are placing 3s, it should be outside 2s. Then 4s, it will be bigger. Okay.
Yeah.
So as you move down the group, what should happen?
It increases.
The
Because
size should increase. Got it?
yes, sir.
Second, third shell, fourth shell, fifth shell. Got it? A
Yes.
new shell is added in every subsequent element due to which the size increases. Got it?
Yes, sir.
How the size of the ions vary? Okay. Ionic radius. So suppose if ionic radius, suppose iodine is there, okay, and I can add electrons to it, and I can remove electrons from it. If I remove electron, what it will become? I plus or I minus?
2+.
I plus, exactly. Right. And if I add electron, it will become I minus. Got it? More electrons, more negative charge, more repulsion. This is the neutral atom. So can you compare the size of a cation? I'm not comparing the cations of different element. I'm just comparing one element, iodine. It's atom, it's cation, it's an ion with its own cation and anion. So what should be the size order, Naveen?
Mm,
Will it be more? Will it be less? And for whom?
positive side will be less, and the negative side will be more.
Exactly. So less electron than the parent atom. Smaller size. And this will have a larger size. Got it?
Yes.
Maybe let's compare the size for iron Fe2 plus, Fe3 plus. Any gradients can you compare?
3 plus would be most and Fe will be least.
Fe3 plus will be?
Oh, sorry. 3 plus is least.
Yes, because 3 electrons are removed. Okay, so electrons removed will cause less repulsion and the size will shrink. Got it?
Yes.
Fe3 plus will be the smallest, Fe2 plus, right?
Yes.
And Fe is the original atom which is having 26 electrons. Got it? Remember the atomic number up to 30. Very, very important. Atomic numbers, right? Mass they will be giving it to you, right? So this is the answer. That's correct. Now I'm going to give you cations and anions of different elements. Let's say suppose if you take Na plus, Mg2 plus, and Al3 plus. I can tell you their atomic number. 11th element is sodium, 12th element is magnesium, and this is the 13th element, right? And you need to tell me how many electrons are present in it. How many electrons? Sodium. Na plus. Will they be exactly 11?
There will be 10.
It will be 10.
Yes.
How many electrons and 10, right?
Yes.
So 2 I remove. And
10.
how many? 13 I remove 10. Very good. Got it. Is it clear?
Yes, sir.
So these species are known as isoelectronic species. Got it?
Yes, sir.
What are isoelectronic species?
The 3 will be the same.
Which have same number of electrons. Got it?
Yes, sir.
But the protons are the same. Protons are different. Why? Because they are different elements. Got it? So 11 protons, 12 protons, and 13 protons. Exactly. So now can you compare? The electrons are same. But will their size, will it be same or will it be different? And if it is different, which one will be the largest and which one will be the smallest if they are different? If they are equal, then they are all equal. There are 10 electrons, right?
Yes, sir.
But the protons are not same.
Yes.
What do you think about the size? Navila, of these elements? Ions of these elements, not elements.
Mm,
Will the size also, there are 10 electrons, right? 2 shells. But it also depends upon how strongly the shells are getting attracted.
yes.
Got it? Inward. If the attractive force is higher, it is more, the size will be less.
Yes.
Is it clear or not?
Yes. The sodium will have.
So which one will be the biggest and which ion will be the smallest one?
The smallest should be aluminum.
The smallest will be aluminum, exactly, because the 13 protons are, the electrons are just the same, but they are not feeling the same attractive force. Absolutely correct. The 13 protons are going to pull the 10 electrons more strongly. Got it?
Yes, sir.
So the size is going to be the smallest. Okay, as you have for isoelectronic species, more protons, electrons are same. So I'm not talking about the electron for isoelectronic species. More the higher the number of protons. Okay.
Oh,
Higher will be the attractive force, smaller will be the size. Got it? So these 10 electrons are going to be pulled by 13 protons and the size will be least. Got it?
yes, sir.
Okay, so this is going to be the smallest one. Absolutely correct. And then you have magnesium, right? And then the sodium will be the bigger. Okay.
Yes.
What about Li plus, Na plus, K plus, Rb plus, Cs plus, lithium, sodium, potassium, rubidium, cesium?
Cesium will be.
The biggest. They are not top, they are neither isoelectronic, they are neither from the same period, they are one below another. So cell is increasing, right?
Yes, sir.
Absolutely correct. Lithium is the smallest in gas phase, right?
Yes.
In water, the size reverts because the water molecules surround them.
Okay.
Got it?
Yes, sir.
Let me ask you one last question. These are also isoelectronic species. N3 minus, okay. Atomic number is 7. You add 3 more electrons, 10 electrons. Then you have oxygen minus 2 oxide ion with atomic number 8 and fluoride. All have same number of electrons. Got it?
Yes, sir.
So what is going to be the size? All the 3 places you have 10 electrons, right?
Uh, yes.
So tell me the size.
N is the smallest.
Which one?
N.
N has 10 electrons. Let me write the protons also. 7 protons, 8 protons, 9 protons. Tell me.
Oh, so 9 protons would be the least.
Which one will be the biggest? Electrons are same, but not only electron count, the attractive force also counts. And who is responsible for the attractive force maybe? Protons. Okay. Look here.
Biggest is
You answered the above question, you answered for the cations very correctly. Okay. So electrons are same, but the force, attractive force is not the same, right? I hope this is clear.
Yes.
So tell me,
Nitrogen.
which one will be the biggest? Yes, it is going to be the biggest. Because just 7 protons and too many electrons. Okay, 10 electrons, more than. So they are going to, and the negative charge is also highest, -3. So the repulsion is going to be very large. Okay, it is going to expand from its normal size, right? Then oxide and then N. So I hope, okay, in isoelectronic species, higher the number of protons, smaller will be the size. Okay, down the group, new shells are added, size becomes larger, it becomes more. In this period, left to right, across the period, the size shrinks because no new shell is added.